Let's solve problem 8.16 for Microelectronic Circuits 8th edition by Sedra and Smith. So we're given this circuit, and we're going to express the voltage from base to emitter for each BJT as 0.7 volts, and we're also going to assume that beta is infinite. We want to find the current I expressed in the figure, V1, V2, V3, V4, and V5, which are all labeled here, for two cases. One where R is equal to 10 kiloohms, and the other where R is equal to 100 kiloohms. Now, I did not cover BJT current mirrors in my lecture video for this chapter, so I will be detailing this circuit. First off, let's try to observe pretty easy voltages, or low-hanging fruits as I like to call them, and solve for those first. So I want to direct your attention to V3. How can we calculate V3? Knowing that the voltage from base to emitter is equal to 0.7 volts. Remember, we cannot calculate the voltage from base to collector, but calculating the voltage from base to emitter is actually very simple. Observe that we are at ground here at Q6, and all we need to do to travel to V3 is simply start at that ground at the base, 0 volts, and just add the voltage drop from base to emitter. So V3 will simply be 0.7 volts. Notice that to calculate this, we did not have to worry about the resistance. Let's find another easy one to calculate. How about V2? How can we calculate V2? Again, if we start at the top, 2.7 volts, and we just travel down to V2, all I have to do is cross one emitter to base at Q3, or Q2, or Q4, because they are all shorted together. So V2 will just simply be 2.7 volts minus the voltage drop from base to emitter. So that would be 2.7 minus 0.7, or 2 volts. Notice again that this calculation did not require any information about the resistance. Now let's analyze Q3 for a moment, specifically the emitter base junction. We see that the emitter has 2.7 volts, and the base has 2 volts, making the emitter base junction forward biased. And let's analyze its collector base junction. So what's the voltage at the collector? Well, that would just be V3, or 0.7 volts. And again, the voltage at the base is 2 volts, or V2, meaning that the collector base junction is reverse biased. Now, why am I bringing this up? This tells us that Q3 is operating in the active region. But not just Q3, in fact, Q3 and Q4 are both operating in the active region because they are shorted. We can also see that they are splitting I. So in other words, this current here would be I over 2, and this current here would be I over 2. They are splitting that current I. And the same goes for Q2 and Q1. They are also splitting I over 2. Because Q2 is shorted to Q3 and Q4 respectively. So based on this, we should be able to calculate V1. We know that V1, if we were to start at this short right here, going from 0 at the base of Q1, we would just do 0, because that is the voltage at the base of Q1, minus the voltage from base to emitter, and that is equal to negative 0.7 volts. Again, notice that this calculation did not require the resistance. For now, let's assume that Q5 and Q6 are also an active region and also equally split the current. So we have I over 2 here and I over 2 here. And let's try to write some equations for V4 and V5. So if I wanted to write an equation for V4, and we're starting at the bottom now, that would be negative 2.7 volts plus the voltage drop across the resistor, which is R. So it would be plus I over 2 times R. And V5 would be very similar, negative 2.7 volts. This time it's R over 2 for that resistance. So that would be I over 2 multiplied by R over 2. Now, I don't know the current yet, so I can't solve for V4 and V5 yet. I have too many unknown variables, but maybe there's another equation I can make. What about V1? I already know what V1 is equal to, and I also know that V1 can be calculated with respect to that resistor R. Specifically, V1 would be equal to negative 0.7 volts, as we know. We can also write this if we go from the bottom of the circuit, it would be negative 2.7 volts plus the voltage drop across that resistor, I over 2 times R. Perfect. Now if I want to move this negative 2.7 volts to the other side, that would make I over 2 times R equal to 2 volts. Or I could say, if I multiply this 2 in the denominator to the other side, IR is equal to 4 volts. So now I have an expression for IR, and I should be able to use this to solve for V4 and V5. So let's leverage this expression, IR equals 4 volts, to solve for V4 and V5. So again, let's rewrite the equation for V4. It's equal to negative 2.7 volts plus I over 2 times R. So this would be equal to negative 2.7 volts plus IR over 2. So this is equal to negative 2.7 volts plus 4 volts divided by 2. So V4 is equal to negative 0.7 volts. And then similarly, V5 would be negative 2.7 volts plus I over 2 times R over 2, or negative 2.7 volts plus IR over 4. So V5 is equal to negative 2.7 volts plus 4 volts over 4, which is equal to negative 1.7 volts. And lastly, in the case that R is equal to 10 kiloohms, we would get that the current, we could calculate that as simply just 4 volts divided by R, using that original expression up here. So that would be 4 volts divided by 10 kiloohms, which is equal to 0.4 milliamps. In the case that RE is equal to 100 kiloohms, we would just do the same calculation, just replace R for 100 kiloohms. So that would be 4 volts divided by 100 kiloohms, and that would be 40 microamps. Now I want to point out that none of the voltages change when the resistor value changes. The only value that changes is I. You might be tempted to think that V4 and V5 change because it involves R, but you can see that we solved it using IR, and R is inversely proportional to I, meaning as one increases, the other will decrease at the same magnitude. And because of that, only I changes when R changes. So that solves the problem. Thank you for watching this video. For any questions or comments, feel free to leave those in the comments section or contact me by email. Thank you and have a great day.